In this video, we're going to derive the push-forward or Jacobian vector product rule for matrix vector multiplication. So matrix vector multiplication can also be seen as a function which takes a matrix A as well as a vector x and then performs the matrix vector multiplication A times x, and then let's call the result of that set, or also vector set. So let's assign some dimensions to our quantities. So A is going to be a matrix which shall be m by n dimensional. Then, since we do a matrix vector multiplication with x from the right, x has to be n dimensional, and as a consequence, set will get the row dimension of A, so will set have n dimensions. Of course, we could also have a square matrix which would be n by n, and then the output would have the same shape as x, but let's keep that here as a rectangular matrix for generality. For the push-forward or Jacobian vector product rule, we shall now be propagating tangent information on the input, so tangent on the matrix and tangent on the vector x, to the output of the computation, which would be a tangent on z. And by this definition, we know that the tangent on z, indicated by the dot, is given as the summation over all the inputs to a function, whereas we take the partial derivative of the function with respect to the input and multiply it with the tangent of that input. So we will have df by d matrix A multiplied with the tangent on A plus df by dx multiplied with the tangent on x. And now we have to be a bit careful, since here we have a quantity derive the function f with respect to A, and since the output of the function is the vector set, this derivative will be a three-dimensional tensor since we are deriving a vector with respect to a matrix. And so using this symbolic notation becomes a bit ambiguous, so it actually makes sense to work in index notation. So let us switch to index notation. And before we derive the push-forward in index notation, let us recall the primal computation in index notation. So the primal computation f of matrix A and vector x will be given as A index ij multiplied with xj, and then this shall be the output zi. And here we are implicitly assuming the Einstein summation convention, so if in a multiplication an index appears twice, we will sum over it. And in a sense, this is what a matrix vector multiplication would do, so it's a legit way of writing that down. Then we can also take a look at the push-forward rule in index notation. So let's do the push-forward rule in index notation, and for this rule we are then looking at the ith index of the output tangent, so we will do set dot index I as a consequence is given of the derivative of, well, f, and here I'll just use the output of the function set I in order to work in that terms. So let's do the derivative of set I with respect to the matrix A. But let me introduce some additional indices here and say we are deriving with respect to AKL, and then we have a contraction by using the tangent on A also with the index KL. And then we also get the index I out because we have the contraction over KL. So we take the derivative of the output with respect to one of the inputs and then contracting with the tangent on that input, and therefore we need identical indices. And then for the second term in the summation, we will have dzi with respect to xk, and then we will contract with the tangent on xk. So in order to evaluate that, let's first take these derivatives separately. So let's first do that derivative. So let me take that here. So the derivative of the output with respect to akl. Well, let's look at the equation here. We have aij times xj with respect to akl. And since xj does not depend on akl, we can just take the derivative of aij with respect to akl. So this is equal to daij with respect to dakl times xj. So in a sense, we're now taking the derivative of this matrix expression with respect to this matrix expression. And so we are getting some sort of like a high dimensional identity tensor, and this can be expressed using Kronecker deltas. So we will get an Kronecker delta in which the indices match. So we will have a delta ik, a delta jl multiplied with xj. Okay, let's do something similar for the other derivative. So d zi with respect to xk is going to be, well, aij does not depend on x, so we will just have aij multiplied with the derivative of xj with respect to xk. And similar idea, we will just get the Kronecker delta here. So aij multiplied with the Kronecker delta jk. Okay, with these derivatives down, we can then assemble again the expression for the push forward. So let me write that down. As a consequence, we will get the tangent on zi is given as, well, this expression, delta ik, delta jl, xj times the tangent, which was a tangent, and then kl, plus the other expression, which will be aij, delta jk, and then multiplied with the tangent, which was xk, so tangent xk. And then let us apply the properties of the Kronecker deltas, which are essentially an index change. So first, let us look at that Kronecker delta, which changes all indices from I to k, or we could also think of it reversely, which changes all indices from k to I. So in a sense, we will have this index being changed to I. So let's have a dot and change that to I here. And then we also have the delta jl, and we could either change the j to an l, or we could change the l to a j, and let's do that. So we will have aij here, and then all the Kronecker deltas for the first product are deleted. So we will just have an xj here. Then same strategy here. We will either change the j to k or the k to j. So here it makes sense to change from k to j. So we will have aij multiplied with the tangent but index j. Okay, then we have that as our output tangent. And now we have an expression that can be put back into symbolic notation. And essentially what we see here is that we have a matrix vector multiplication where x is again multiplied from the right, but this time we use the tangent on a, and here we have another matrix vector product. We use the original a, but multiply with the tangent on x. So let's go back to symbolic notation, and in our case, that would mean we have the vector tangent on z is given as the tangent on matrix A, matrix vector multiplied with vector x, plus a matrix vector multiplied with the tangent on x. And then in total, we can get the push forward rule on our function. So the matrix vector multiplication given the primal inputs matrix A and vector x, as well as tangents on the inputs, so an a dot as well as an x dot. Then the result will first be the primal computation, which is given as a times vector x. And then we can propagate the tangent information by using a dot times x plus a times x dot. So essentially the rule we figured out here. And then we identify here, this is nothing else than the output vector z. And this is the propagated tangent to z, so z dot. And this is our forward rule for matrix vector multiplication. A big thanks to all the patrons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you will find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. There's more content on automatic differentiation here. Here you will see similar videos, and I hope to see you in one of the next videos.